Good morning. Good morning.
Good morning, Professor Simone. So we have Dr. Meng, yes, and Dr. Shabudin. All right. Okay.
Hi, nice to meet you.
Nice to meet you.
All right. Shall we start now?
Yeah, whenever you're ready.
Yes.
I don't know how I can share my screen.
Share screen. At the bottom of WebEx, we have mute.
Yeah,
Stop.
I think that's not enabled, so I guess somebody who controls the meeting needs to give me authorization.
Oh, I see.
Yeah.
Hang on.
Okay, Prof. Simeone. Yes, is it correct? And you're now present. You can start sharing now.
It's still not enabled. I have the grade.
Okay, my technician is telling me that they will allow you to be the presenter in order to share your PowerPoint slides. Just
Again, as soon as the share button allows me to.
all right. Just give him 1 minute.
Hello, I'm here, Professor Rafiq.
Shabudin, the technician is trying to solve one problem so that our speaker can share her file. Okay.
Prof, I already changed your role into presenter. I think there should be no issues to share your slide now.
Yeah, unfortunately, I just get a grayed out button for the share at the moment. Shall I log off and log back on? I don't know.
Okay, yeah, let's try that one. Yeah.
All right. Yeah, unfortunately, it's still not appearing. Let's see. I could send you my slides, but they're also be a little. I don't know what else to do here. Usually it works. So.
Hang on, let me call my technician.
Maybe you could test giving sharing privileges to somebody else to see whether the problem is just my connection or what. Okay. Maybe I'll try again. I just modified some security settings. Hopefully it will work. Okay, it seems to be working now.
Is it working now?
I think so. Yeah.
Oh, right. Okay, that's good.
Yeah, I think different security settings. Okay, I think we're in business.
Okay, excellent. It works. All right. Okay, let's start.
Okay.
Bismillahirrahmanirrahim. Thank you. Assalamualaikum. Hello, welcome everyone. Welcome to our 66th UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I am the Dean of Engineering University Technology, Malaysia. Today, it is my utmost pleasure to welcome our distinguished speaker, Professor Simone Hochgreb from University of Cambridge, United Kingdom. A bit about our distinguished speaker today. Simone Hochgreb is a professor of engineering at the University of Cambridge since 2002. She obtained her PhD in mechanical and aerospace engineering from Princeton University in 1991. She was the principal investigator in MIT and Sandia National Laboratories from 1991 to 1999 and 1999 to 2000 respectively. She subsequently worked as managing engineer with Exponent Incorporated USA from 2000 to 2002. Professor Hochgreb's research mainly focuses on energy conversion and reacting flows, aiming to gain a profound understanding of the physics of reacting flows in energy conversion devices and the trade-offs in stability, efficiency, and emissions. Many of the projects involve experimentation and analysis at realistic conditions, from which simpler experiments are defined. Measurements in gas turbine injectors at pressures and temperatures provided the questions for current experiments investigating how reactant stratification behavior affects flame structure, emissions formation, ignition behavior, and instability. So that is a brief biography of our distinguished speaker. Here now is Professor Simone Hochgreb from University of Cambridge, United Kingdom, with his talk on narrowing the gap between experiments and models in turbulent reacting flows. Professor Simone Hochgreb, over to you.
Thank you very much, Professor, for the kind introduction, and apologies for the initial technical problems here. I assume I am talking to engineers, practitioners in the area of energy in general, particularly the area of combustion. And this talk, I'm doing sort of a review of where we are in terms of understanding reacting flows and how well we can make predictions of that. And in particular, for those of you who may not be very familiar with the process of how do we go about validating models that various practitioners would come up with for turbulent reacting flows, what kind of data do we generate? So without much ado, I'll just plunge in, and hopefully people can see my mouse moving about. Is that okay? Okay, good. As we all know, about 90% of our energy use still is dependent on fossil fuels, whether we like it or not. Obviously, we're trying to reduce that dependence, but that will take many decades. And in particular, when we talk about mobile sources such as engines and airplanes, those will be continue to be in large part using fossil fuels. So we still have a ways to go in terms of, let's say, removing ourselves from fossil fuels. What we're trying to do is to improve the efficiency and minimize emissions in all cases, but different devices have different, let's say, specific needs. For example, when we talk about, when we talk about engines, this is typically an unsteady device, which might have water ignition and operates at very high pressure. And what we're trying to do is maximize efficiency and minimize the emissions of soot, NOx, and CO. If we talk about gas turbines, the problems are slightly different. We're talking about minimizing the probability of blow-off and instabilities. Typically, we'll start with liquid fuels and sprays, but again, we want to minimize soot, NOx, and CO. And then we've got furnaces that burn biomass or coal and so on. The problems are slightly different. This is kind of a steady state device. And what we're trying to do is to get it to radiate and transfer well to a boiler, for example, but we still want to minimize the same kinds of emissions. So some of the problems are similar, some of them are slightly different. So what we're trying to do is to create a situation where we have a statistically steady turbulent flame, because obviously turbulent flames are not steady. And we come up with measurement techniques which are instantaneous that can give us something about the statistics of these scalar measurements, velocity measurements. And from that, we try to infer how the turbulent flame structure evolves and benchmark the models so that we can make good predictions of the emissions. So I'll take you through that. Now, what is the problem with turbulent combustion? Well, obviously, it's turbulent, and what that means is that there are turbulent fluctuations over a range of length and time scales. So you could have a flame which is statistically steady, it sits in the same place over a long average time, but every shot will have lots of fluctuations. Taking a look at, for example, how a premix flame looks like in a microscale, we can see that there's a thickness to a flame. This is an image of the temperature of the flame, which typically is of the order of tens of microns. And then there will be an eddy, which are these structures. They are moving the flame around. And that's what we call, on average, the integral length scale. And those can vary over a reasonably wide range of the mixture. Now, turbulence has this interesting way of behaving where, you start out with a large scale, typically the scale of the device itself, which we call the integral length scale of turbulence. And the turbulence cascades all the way down to the small scales. And in fact, there's a relationship between the velocities and lengths at the large scales and at the smallest scales here, which would be the viscous scales, where eventually it disappears. And that's what creates some of the difficulties in turbulence, because we have a very large range of scales that we have to resolve. And we have turbulent combustion. You have an extra scale, which is the scale of the flame that you like to resolve. The plot that I have here on the left is a typical plot of how we represent the kinetic energy of the turbulence per unit wavelength, or 1 over the length scale, in this spectrum here, which is typical of turbulence. And this is a non-dimensional scale, non-dimensionalized to the smallest scale, which is the viscous scale here, called the Kolmogorov scale, which we usually cannot measure. And the largest scale, which is the scale of the eddies, which usually we can measure. And between those, you can see that depending on the Reynolds number, there is a relationship between the largest scale, smallest scale, which tells you that that range goes as Reynolds number to the 3/4. So obviously, if you go to typical Reynolds numbers, that would be of the order of 1,000 in realistic devices. We're talking about a very vast range of scales that we have to resolve in a calculation. And the length scale of the flame, for example, might be of the order of tens or 100 microns or something like that. The Kolmogorov length would be of the order of microns. And then you have maybe centimeters to meters scale of the integral length scale. Now, when we do a calculation of that, how would we try to resolve that whole range? Typical scale range would be from the micron range to the centimeter or meter range, for example. So that's a very vast range of orders of magnitude here, maybe 4 orders of magnitude, 5 orders of magnitude. And likewise with the time scales under which this operates, so very slow processes and very fast processes. Typical validation experiments and the techniques that we have can resolve at best 100 times. So if you have an image, for example, you could resolve the smallest scales and then maybe 100 times that, 100 by 100 pixel image, if you imagine something like that, or 1,000 by 1,000. And likewise, time scales we could resolve, for example, millisecond down to all the way to second, but not the whole range of orders of magnitude. So there's always compromise, and that's why we need modeling of these processes, because we can't resolve everything that's going on. Typically, what goes on in turbulent combustion is depicted in a picture like so, where we have the length scale of turbulence normalized by the flame length scale. And on the other scale, we have turbulence intensity normalized by the laminar flame speed, for example. So at the bottom range here, at the bottom range here, where we have very small turbulence and very small length scales, everything is laminar, and we can resolve what goes on there. If we go to larger length scales, but modest levels of turbulence, then these are relatively wavy flames. They can still be resolved. But as we go to more realistic behavior of the turbulence, then the flame starts getting disrupted all the way up to where you cannot tell where the flame actually is. You shred it. And those regimes are very difficult to try to resolve, and we can only do that in a statistical sense. Oh boy. Looks like we lost the screen. Let me try it again. Here we go. Okay, we're back. Okay, so now we can resolve it. We can solve Navier-Stokes equations with the reacting flows and do a direct numerical simulation, DNS. But typically DNS is good at resolving high levels of turbulence, but not large domains. That's typically what limits what happens there. So at most, the largest calculations resolve maybe 10 flame thicknesses, not too much more than that. But of course, our devices are much larger than that. So that's where the models come in. So a lot of the devices will operate somewhere in this range at high levels of turbulence and large length scales. And yet the experimental evidence that we have where we can actually validate the models is, again, somewhere in between. So there's a lot of compromise between trying to resolve the overall problem and interpolating between where we want to be and where we actually can have a model and get some statistical averages of what's happening in those problems. So that's where the modeling comes in. I won't bore you with too many equations, but typically when we're trying to resolve turbulent combustion, what we're trying to do is to resolve scalars on a range where we have a scalar. This could be temperature, for example, or a species. And we have an equation for the conservation of that. What we try to do is that since we can't resolve that for every instance, we average that in some sense. And that could be just a straight out averaging, which would be Reynolds average, or it could be a filtering operation where we're talking about large eddy simulations. In any case, we have an average, which is represented by this tilde here, and the great discussion goes on in how to resolve these filtered terms in some way via a model. And both the transport terms, which are these two terms here, and more importantly, the reaction terms, which is typically not clear how to resolve this averaging here. What kind of average do we mean? What kind of probability distribution functions do we have? And of course, because we want these models to be cheap, we want maximum accuracy and a number of scalars. So we want to represent not all the scalars, but find out relationships between the different scalars, the species, concentrations, and so on, and temperature, to minimize the size of the computations. And there are various model families that would do that for us. For example, one way to group this is to think about the model as a series of waves that propagate that. And the model, typically we're talking about a reaction diffusion wave, premixed or a diffusive flame. And we then map out how the different terms, for example, the chemical source term, the species, and so on, how they're connected with typically two different variables. One of them we call mixture fraction, which is essentially how much carbon is there in the mixture, so how much fuel was there as it burns. And the other one is what is the local temperature. Depending on the model, this could be just a single connected set where the mixture fraction is fixed, for example, for a premix flame, and the only coordinate is enthalpy. But in more realistic cases, those are independent. And there's a whole other series of models where we look at the mixture not so much as a wave ensemble, but as a micromixer. So, in each cell, let's say, there's a mixing reaction box, and then there are different laws, different models that are applied to how mixing and reaction takes place in that box. This is the picture, for example, the probability density function of mixture fraction and enthalpy, and then using that probability. Thank you. Carry on. That was a very nice interlude of music. Okay. So these models are then, let's say, get built from a whole series of processes, starting from models for the chemical kinetics of the fuel, thermodynamics, molecular transport, and if you have sprays, particle droplet distributions. And you can have a very, very detailed model with very full kinetics, thermodynamics, molecular transport, and so on. But there's a trade-off between computationally how many species and detail you can have in the model and the number of cells. So if you're doing a very large computation with a large number of cells, typically it's not possible to have this much detail. The calculation is too slow. And that's where the models come in. Now, the models are able to take, for example, chemical kinetics that might take a whole manifold of hundreds of species and thousands of reactions to something smaller, maybe that will reduce the overall manifold to a handful of species, and all the other species are then dependent on a known way, depending on the model. So now we only solve for a reduced number of scalars, typically temperature and mixture fraction, and maybe a few others. And then this becomes a much easier problem to solve. Now that we have a reduced number of variables, we can take the number of cells to a larger number of cells and solve a more realistic problem. And eventually we get to some sort of average model, could be LES or RANS model, which then can be tested against either turbulent experiments or against something in a real device, typically. Okay. The order of magnitude of those numbers typically would be, for example, we could be dealing with thousands of species and reactions in cells. That's still feasible. Yeah. But if we go to a large number of cells for a practical device, typically of the order of millions, then we can only take maybe one or two of those variables. And that's typically how today the computations are done. So if you have an LES computation for a gas turbine combustor, that will be maybe tens of millions of cells and maybe two variables, whereas DNS calculations, including chemistry, might have partially full chemical kinetics, but only maybe 1,000 cells. And then once we have the computations and some experiments, and I'll tell you about the experiments in a moment, then we have some sort of validation feedback loop where we have a problem with a given geometry and boundary conditions. We measure a number of these signals, could be species and temperatures and so on, or velocities. And then likewise, we'll replicate that into a model, which will have likewise boundary initial conditions, mesh and filter size, and then choices about the chemistry and a variety of constants that go into the model that gets put into a solver, and then that will turn out the scalars that then can be compared to the original system that we had. And that's where we have our comparison loop here. Depending on how well this goes, we can, well, revise the model and maybe try a different set and see how well that compares. And occasionally we also go back to the experiments where there was something that we forgot to pay attention to the details and they turn out to be important in the model, and so we have to do it again. Now, of course, this is not a new problem. You know, we keep doing experiments and validation. This is not a new idea. What we have been doing in the present is trying to get more efficient at doing this loop. So in the rest of the talk now, I'll talk about what tools do we use for making measurements, how these various experiments and models are currently, what's the state of the art in terms of comparisons, where are we going with these emerging methods for comparisons, and then where are we going with making those measurements. So let's talk about how we measure. Typically, we have different levels of difficulty of kinds of measurements that we can make. Because they're turbulence, they all have to be instantaneous or in a very short time scale. Particle image symmetry is a tool that we all use for making measurements, and these are the simplest types of measurements that we can make. They can be resolved down to microns and very small time scales, and they're not terribly expensive, and many labs have those. So those are typically the entry level experiments, and they're typically very accurate as well because they depend on correlations rather than calibrated type measurements. Likewise, laser Doppler anemometry can be used particularly for sprays. We can make measurements of droplet sizes and velocities. It's the same order of magnitude in cost, and typically it's just a point-based measurements, whereas the PIV, you can take a full image, but the LDA would have a larger dynamic range in terms of the time scales they can measure. And what scalars can we measure? Typically, we have measurements that are made using scattering type measurements, meaning we bring in laser light, maybe excite some species using fluorescence, or simply the scatter of those measurements, and excite the Raman transitions, for example, and that can give us different types of information that we have to. Yes.
Nak bertanya sikit boleh tak? Okay. Ni pasal external examiner berapa orang dah selalu lupa dah itu. 3 ke 5 ya? 3.
I don't. Sorry, I can't understand it.
Dia bukan staff. Oh 3-3. Oh bukan 3-5. Oh silap. 3-3 itu saya kena buang sebab ada satu student saya tu Alah Nur Farah. Saya dah masukkan nama tapi tak wani submit lagi. 3-3. Nur Atikah. Nur Farah Atikah. Saya dah masuk dah tapi saya tak submit sebab nak confirm dengan ni. Dia seorang mesti profesor. Okay.
Hello? May I continue?
Kalau antara dua mesti ada 2 profesor macam mana? Maknanya kalau luar profesor, dalam tak payah profesor lah. Oh jadi salah seorang tu mesti profesor lah. External atau internal mesti profesor salah seorang.
Sorry, I don't speak your language.
Oh, dalam profesor. Oh. Oh, jadi nanti jadi maksudnya kalau di luar nanti dia pilih external examiner seorang profesor, di dalam ni internal profesor mania pun tak apalah. Sebab dia akan pilih seorang kan. Okey. Terima kasih. Hello. Ya. Oh tu kah?
Okay, I'll try.
Sorry. Masih. Jadi aku kena off kan lah. Okay.
Is it possible to mute all but the speaker? That would be helpful. Thank you.
Yes, please, to all of you watching this webinar, can you put yourself on?
The host can mute everybody, I believe.
Right, okay, yeah. Thank you.
Yeah, okay.
You can continue,
All right.
Prof. Sorry about that.
Sorry to carry on. All right, okay. So there's a number of techniques that can allow us to make instantaneous measurements of species. From that, we can build mass fraction, and we can also build temperature maps. These are not simple techniques, and they don't work under all circumstances. So there's a whole range of choices, but typically we are able to measure, for example, temperatures, selected species such as OH, which is a key species in combustion. And in some cases, we are able to measure all the major species using Raman, and these are not trivial techniques to obtain good measurements from. And finally, there are techniques that can work in the very radiant conditions that we have. For example, especially if you have sprays or particles, it's quite difficult to make these measurements because the flame itself has a lot of luminosity. So spectroscopic techniques can have a lot of trouble discriminating. But coherent techniques, what we call, where the output is a laser beam as well, allow us to separate the species measurements from the background luminosity. But these techniques require quite specialized equipment and techniques to, and therefore they're not very popular. There are very few measurements using those techniques in general. Okay, so this is the suite of different types of techniques that are used for turbulent combustion measurement. And then we had to think about what's the right way to set up a validation. Typically, one would wish to design independently of the modeler so that it's a true test of the model. Often this is not possible because the modeler and the experimenters should communicate about what is possible to measure so that appropriate adjustments can be made. You should always have well-characterized boundary conditions because those often affect the overall measurements, and to the extent possible, clear experimental uncertainties. And then we try to build in some sort of hierarchy of complexity where we make the simplest possible measurements, for example, non-reacting validation, and then eventually build up to a more complex set of experiments, as well as testing the models over a wide range of operating conditions. Now, ideally, we would test the submodel directly, as in measuring probability distribution functions or reaction rates. But that's often not possible because all we can measure are typically the scalars that I told you about. So we have to find indirect ways to test the model. Now here's a list of a number of experiments that have been made over the past 20 years or so for purposes of validating turbulent combustion models. Most of them have been in some sort of jet plane, either piloted or not piloted, over a number of institutions with the capabilities for making measurements of temperature, species, velocity, OH, and NO, with fuels that don't vary too much over a relatively narrow range, and typically gaseous fuels, so we don't have a lot of information about liquid fuels. Typically, these are either premixed or stratified measurements, meaning the fuel concentration is constant or not. And some of them are representative of actual burners in gas turbines. And I'll show you some examples of those. We call them technical burners. There are measurements made specifically for understanding soot, which is a very complex chemical process of building up soot. And then there is a number of new experiments where we're trying to tackle the problems of spray combustion, which is quite a bit more complicated because the flames are more luminous, and now we have to measure the droplets, and the fuels are more complex. And then finally, there are a number of flames which were done for coal and biomass and so on, where these measurements, again, are rather limited because of the complexity of the fuel from solid to gas and on to other species. Once we have the data, then the data gets disseminated in a number of data exchange networks. So, for example, what started as the turbulent non-premixed workshop is now sort of a data exchange for flames in general. There's one for engines, there's one for solid fuels, and so on. And those are excellent forums for exchanging information, and there will be a database on the web that models can be tested against. So let's talk about some of those data and some of those databases. The TNF workshop flames started from simple piloted flames all the way now to a whole range of practical burners, stratified burners, and so on. And it keeps going. All of this is still at ambient conditions, in part because it's very difficult to get data at pressure. But I'll tell you about some of the data at pressure as well. This particular flame is one of the most tested against, is a whole, and mostly because it's a very complete data set. You can see here there's a flame, there's a small jet in the middle, and then there's air on the outside, and then there's a pilot that can keep the flame lit over a very wide range of turbulence ranges. And these are the flames as you vary turbulence. And you can see they all have the same characteristic here, where mixture fraction, which is essentially the total amount of carbon hydrogen weighted for the fuel as a function of temperature. So an ideal diffusion flame follows this line, and you can see that most of the flames, so long as the Reynolds number is relatively low, follow this model. But at some point that breaks down, where there's quite a bit of extinction, and now the flame no longer follows that behavior. But the reason this flame is, the model is the database is very popular, is that it has a complete set of temperatures and species, including some of the minor species such as CO and NO and OH. So it's a very valuable database for testing your model for turbulent diffusion flames against the data. Typically, most models are able to capture the species, but capturing the behavior of NO, which has very slow chemistry, that requires special treatment, either by separating it instead of the manifold of a diffusion flame that's treated separately and calculated as a separate equation on the scalar. And then one is able to make the predictions that agree with the measurements. Another set of flames is when we relax the assumption that it's either a diffusion flame or a premixed flame, but somewhere in between. There are 3 different flames that have been considered in these different networks, and I'll talk only about the last one, where there's actually fuel and air that come through the inside, and then a pilot flame on the outside, and the pilot can go up and down, varying the amount of mixing that there is, and that produces a rich flame on the outside and a lean flame on the inside, which has some interesting characteristics. So let's see how models do against those kinds of flames. So you can see here a number of predictions from different models. Each color line is a model, and the data are the little black points. And here we're showing mean temperature as a function of location. And this is the mean fluctuation. And we can see that for this is 5 diameters from the beginning, and this is 10 diameters, 20 diameters. You can see that things start very well, and then very quickly the models start deviating from the experiments and from each other. So that's where there's a lot of disagreements. The models are different, and some of them are better than others. And this is where the process of feedback loop goes on. People go back and revisit their models to try to see whether they can do better. 2 years later, you can see how the comparison went, and you can see that there's still not complete agreement, but things are looking a little bit better. This is a different data set. This one was, where we're looking now at the carbon monoxide instead of temperature. And you can see again that when there's discrepancies, or there are discrepancies in temperatures, that magnifies the discrepancies in CO as well. So we can see that we're still a factor of 2 from the true value, and different models do differently. And you can see that there's still a long way of agreement of that. There's improvement that's still necessary. Now, that was for model type flames where loads of measurements are being made. What happens when we have something that looks like an actual combustor? And this is a measurement that was done at DLR in Germany for something. You can see there's an injector with fuel and air and spill generators, very much what you would see in a real combustor. And this was based on a real combustor. And there were measurements made at different locations here of all the species and simultaneous temperatures, and see how that maps out onto the temperature mixture fraction map expected, for example, of a diffusion flame. We can see that there's some regions in this combustor here, this one at height of 15 millimeters, where things kind of behave as a diffusion flame. You can see many of the points are on this manifold here. But still, there are many more points that don't fit that particular picture. This fits more maybe a premixed flame with a fixed mixture fraction, or all over the place, all sorts of mixture fractions and so on. So it's a much more complex problem than the original one. The desire, of course, would be to have instantaneous mixing and premixed flames, because that would produce the lowest NO. But of course, this is not always possible. Let's see how the simulations fare against this data set. We can see that once things are completely burned in the far field, that behaves quite well. And this model in particular picks up the temperature behavior reasonably well, but it doesn't do so well, for example, for CO and hydrogen, which are obviously important from the point of view of making predictions of pollutants. Here's another data set from a Siemens combustor, which was tested again at the same facility at DLR at high pressure, where here there are measurements being made using these windows in different locations axially, and that's tested again against some full LES of this technical combustor, which is partly premixed and part and lean. So you can see here again on the manifold, it sort of follows what a diffusion flame would do, but also there's many points that don't follow that particular manifold. There have been a number of challenge models to try to match the experiments. Here's a set where a number of different models of those subsets that I showed you before are tested against the mixtures. And you can see that sometimes that agrees reasonably well, but there's no model that captures everything completely well. For example, the red one here captures the temperature reasonably well, but it's off on the CO2 predictions here. There have been a number of recent simulations of that same data, and in this particular set, they were testing different kinetic models and different closure models of that. And you can see here the quality of this is the experiment. This is only for temperature. And looking at the various trials here with different types of models, the major species and temperatures are predicted typically within 10%, which is not so bad. Where it starts to fail are predictions of CO and NO, because they typically are slow reacting species, so the full kinetics and to treat them separately. And here you can see a series of different submodels that were tested against it versus the experiment. And you can see that in general, that doesn't capture the model behavior very well. And the reason for that is that these species are very sensitive to details of scalar fluctuations, especially the temperature. If we look at soot, another very important set of pollutants, let's see where we are on models. There have been good experiments that have been produced, typically on a jet flame. You can see a very tall jet flame here with methane. and good instantaneous measurements were made of temperature, and the models typically captured that reasonably well. Since then, there have been more experiments on that and more attempts at trying to predict the soot. And you can see that the major scalars are well predicted, but the soot itself, very difficult to predict. We're, in some cases, a factor of 10 off from the model. And that's, again, because the chemical models are complex, and there's a whole history that has to be computed. It's very sensitive to intermittency and so on. So there's still very much work in progress. Here's another set from experiments that were done again at DLR of acetylene soot formation with a number of different models. And here's the soot volume fraction being predicted. And you can see that in principle, it looks like if you scale everything, the model seems to capture where the soot is being produced. When we look at the absolute values, you can see that the experiments are very far from the experimental, the models which are being attempted. So that's one of the hardest problems that exist. Some of the reasons for that have been recently explored in other experiments that have been made in this flame, where these are measurements of PIV and OH. And these are the LES pictures, which you can see are reasonably accurate from the point of view of picking up the characteristics of what actually happens, even though they're not quantitative. And what happens is that you have some lean pockets, this LBG here, and then rich pockets. In the rich hot temperature pockets, you produce soot, and then in the lean pockets, you consume soot. But these are very long processes that happen within the flame, and that means that the models have to follow the history of these particles in order to make predictions of soot. Okay, I'll just skip that. And then finally, there are sprays, which now have the complication of not only having the complexity of the chemistry, but now droplets as well. There have been a number of good flames against which models can be tested. These are some of them. I'll talk about one of them that had a good complete data set that was produced from the Delft group. And you can see here how these direct flames so this is a pilot flame on the outside. In some cases, we have a hot pilot, and in some cases with air, and let the flame essentially light itself. And what we see is that if we take the hot pilot flames, it's easy to make a prediction of temperature, and the predictions of the droplets are not so bad. But for the airtight flames, you can see that the model and experiments are quite far, because it's difficult to predict the live here. So it's still, again, work in progress, and more experiments are desirable on this front. There's a new data set coming out of the French, where they are measuring now a technical burner with sprays in the middle, and you can identify the structures as well as the droplets. So here you have the LES measurements on the right, and then the experiments on the left. And it's a good similarity of what happens in these flames. Typically, the fuel vaporizes, and there's a lean premix flame on the inside. Then some of the fuel vaporizes and produces an outer diffusion flame. So there's two flames in one. It's a reasonably complex situation, but the LES model starts to capture what goes on in this overall picture. Now, getting to the end of the talk, we want to talk about quantifying error and uncertainty. Obviously, I showed you some of these plots of how the models and experiments do not agree. But ideally, what we'd like to know is whether we're doing better or not so well as we go along in time. So we need some sort of metric for how well we're doing. So let's take a look at that. If we compare, for example, the PDF distributions of species that we measured, it might be a more accurate measurement than just the mean, and one can do that. And we can think about that as a metric of the distance between this PDF and this PDF by taking some sort of, for example, square metric of the total error. That's one way to do it. Here are 10 LES calculations with different models, but now tallied with a single metric. And we can see that different institutions did different calculations and then were tallied against that metric. Of course, the ones that the worst also will have worse PDF measurements, but at least this has the ability now to capture in a single metric how well the different models are doing in the prediction, each one of the scalars. Another way of thinking about how to use the data in various models is to think about it on a time basis and see whether we can use the experiment to now drive the calculation. For example, in this study, what we're looking at is a situation where the flame is almost being extinguished and eventually goes on to be extinguished. And this was a measurement of OH and simultaneous velocity. And how should we do that? The idea is to take a measurement at a particular point in space and reinitialize the calculation using the actual experimental information in that control volume. And then seek out whether, given that experimental state, whether the state can move to an extinction. And that's something can be done with something called Kalman filtering, which is you do many simulations and then you look for one that might match that particular situation or closely match that particular situation. Then that situation is assimilated into the simulation and then we watch it evolve. So here's the measurement. This was done with OHLIF and PIV. And then the calculation is made to be forced to where the measurements are, which is where the points are. And then we watch what happens to see whether we can observe an extinction. This is baseline measurement. This is the experiment. And then one sought this particular window, which appears here. And this is an experiment where an image that looks like that was found. And then we watch the extinction event unfold, because obviously that allows us to understand how flames extinguish. So are we done with that? Well, we can see that if we take some of these flames, we went from, over a period of 20 years or so, 15 years, from something where there was a lot of discrepancy, and now everybody knows what works well for that flame. But this is a very lengthy process that not necessarily the most efficient. How can we improve this feedback loop of how the models evolve to the best answer? Obviously, I talked about having open databases is one situation where we can improve, but we need to do better in terms of systematic experimental database sharing, systematic and possibly anonymous comparisons, systematic error quantification, and then creating and maintaining standard targets and methods of comparisons. Not only that, but then sharing what's the best practice and the best solution for understanding these systems. This is relatively common in computer science problems, weather forecasting in some fluid mechanics communities, but not yet in the combustion community, although that's moving along that way. The final idea that I'd like to leave you with is that even though we're doing more and more complex problems, we still don't know some relatively simple things. So in 1948, Damkohler ran the first measurements of laminar of turbulent flame speeds, and in a very simple way. It was just a quartz tube with propane and oxygen propane, and he just measured the total flow rate and the photographically obtained flame area. Of course, he couldn't go into the lean range because the flame didn't quite survive there. And those measurements are still all over the place, and there aren't many of them. We just did a review of all of that data. You can see that there's an order of magnitude between the experiments that were done from a number of different measurements. So we're still not there in understanding what's actually going on in turbulent flame speeds, and perhaps that's something that we should revisit. There's a number of particular experimental issues, for example, different standards used for the length scales, different isosurfaces for the projected area. So even though we've made a lot of progress in simulating and doing LES and so on, it seems like we need to go back to some very simple experiments and revisit that and try to do them again using modern techniques. And that's one of the things that we're working on right now. So I hope I have communicated roughly where the field is in terms of measurements and experiments, as well as some of the needs that exist in the field. And I'll just leave that slide there, and I'm happy to answer any questions.
Okay, thank you very much, Professor Simon. Is there any questions? Okay, thank you very much, Professor Simon and Professor Rafiq. We do apologize for some interruption today. Professor Simon really apologizes us. Okay, so is there any question from the audience today?
There is one from the chat. From
Yes.
Prof.
Simon, how would AI facilitate in reducing the gap?
Say it again, please. I can get it. Is it on the chat? Maybe I can.
Yeah, it is on the chat.
Yeah.
Question by Sharifah Kamilah Yusuf. Unmute. Prof. Rafiq,
Yes.
I think Prof. Simon is on mute. Can you do something to unmute?
Well, I'm not the host. I need to call the technician. I will inform the technician.
I just unmuted myself.
It's okay now.
Everybody had been muted. Okay. Yeah, I mean, the answer is there, you know, in terms of what we need databases that are open. We need more data. We need more immediate sharing rather than the cycle of 2 years where we share with people. We need, let's say, more automated ways of storing the data and having people reuse the data for a variety of different processes. I think that by and large the community is doing that, just not quickly enough, because typically the job of sharing is not a funded project. You know, people get funded to take data, but not necessarily to share that on a permanent basis, let's say. So that's been one of the difficulties there, and that's why, to some extent, it's been hosted in places that have more permanent funding. So, for example, at Sandia and now at Darmstadt and so on. And DLR has been very good at also producing and sharing some of this data. It's still hit and miss. But, you know, I think there's progress being made. There's let's say a fear of sharing models and so on, but being put on the spot. But that's how progress is being made. You know, once you see what works and what doesn't work, then you're able to copy what works better and move on.
Okay. Any question from the audience today?
If there are any questions from the audience, you can start your video and click unmute. Or you can use the chat if you want to, of course. Perhaps Dr. Shabuddin can ask a few questions to Prof. Hochgreb.
Okay. We wait for the audience. Dato'.
Do you have any collaborations regarding your wind tunnel low speed wind tunnel?
So far, no. But we do have Dr. Cheong, who performed a similar research with Professor Simon in Cambridge. Okay. So Dr. Cheong.
So Dr. Cheong is there with you?
Yeah, Dr. Cheong now.
Okay. Okay.
Okay, Dr. Cheong, you want to say something?
Yeah.
Dr. Cheong, okay.
Hello, Prof. Simone. Hello. Uh, do you think that the emissions data is adequate enough for the validation of for the frame model? I mean,
Yeah, I think for some cases it is. If you think about, there's reasonable data for carbon monoxide and soot. You know, there's the soot workshop, International Soot Workshop, which meets every 2 years, and they maintain a database, particularly with PLR, and in Australia, the Adelaide group has been very good at maintaining that. So that's a really good database, and now DLR is producing a high pressure database as well for soot. For CO, there are, usually the data sets that include Raman is reasonable. There isn't a lot of data is NO, because those measurements are harder to make and harder to make accurately in absolute terms. So there's plenty of room for good measurements of NO.
another thing is, would it be if I validate the emissions only, and would it be over interpreted if I talk and do perform some analysis on the flow field of the flame? I mean, if I manage to if I manage to validate the emissions only, I mean the global emissions, uh, would it be would it be would I overinterpret the data if I talk too much about the flow field from the CFD?
Well, they're independent things really, because if you do CFD and you get good agreement, that's great. Yeah. Is it a coincidence or not? Yeah, because usually there's a few constants as well. So that's where typically, ideally, you validate it against a larger set of data established databases. So the idea is that, getting good agreement with NO, it could be that nothing else agrees very well, but you use the certain constant for one of the models, and that perchance gave you a good agreement. So you always need to have both. So if you have good agreement with temperature and you get good agreement with NO, well, then you're on a good track. But if you only have one, then that's more difficult to justify. Yeah.
Okay, thanks. I'll open up to the rest for the questions.
I've got a question. Farid here. Farid.
Yes, Farid. Proceed.
Hello, Prof. Simon. I'm Farid from Mechanical. I think we've met last year.
Okay.
I went to your lab.
Yes.
Prof, I believe you've done quite extensive research towards the combustion, emission, spray, and some of the research related to as well internal combustion engine. How you see the internal combustion engine technology compared to I think recently a lot of car manufacturer or engine manufacturer more towards the electric vehicles. So how do you see this future technology?
I've done work before, but this is I'm not following the detail of what's happening now. But it's very clear that not too long, all engines, the internal combustion will continue to be used, but most of the development will be in hybridization. Yeah, so partly or fully hybridized engines. There'll be much higher penetration of electric vehicles. So, and that's all good. But what that means is that there will be even more problems to work on for hybrid engines. For example, people didn't worry about engines that work only once in a while. And yet you now have a situation where you can have hybrid engines that hardly ever work.
Yep.
The engine itself doesn't work because it's potentially a plug-in hybrid and so on, and then all of a sudden it has to work perfectly, right?
Yeah.
So this is an issue. You're going to be talking about engines that are smaller in size,
Yes.
and highly pressurized, which has its own problems, which were not typical problems before. So pre-ignition, which didn't used to be a problem, is a problem for very small, highly pressurized engines. So, and we haven't completely cracked, and I think there will be a merging between what we now see as diesel and gasoline. There will be diesel kind of engines that will operate with turbocharging, just because they're more efficient and cleaner. So I think that's coming. There's prototypes, and there are many people working on that. Part of the question is whether there will be a faster move towards electric vehicles, which will overtake the developments in hybrid, because there's so much more acceptance now of electric vehicles,
Correct.
which are produced very, very quickly and with good quality, and the price is likely to come down.
Yeah.
Which for many users will solve. If you're not a long commuter, this is fine. And so there will be a parallel development there of engines that are hybridized and electric engines, which eventually will probably, let's say, eliminate, not completely, but the volume of IC engines will be smaller and smaller. So any interesting changes, I think all for the good will come. Of course, now we have to think about who's going to produce where is all the electricity going to come from? Is it going to come from all renewables? What kind of renewables? Where? Or will it be from some of it with fossil fuels as well? So, as much as we would like to solve the greenhouse gas problem immediately, that's unlikely to be solved immediately, because the evolution and the investments that are required are substantial. Yeah, so things won't disappear all of a sudden. Oh, we'll never do IC engines again. But yeah, it's a new world, especially after COVID and lockdown, and people learning that they don't need to commute. That would change the picture in transportation quite a bit. Yeah.
Thank you so much, Prof, for your detailed answer and your feedback. Thank you so much. All right.
Okay.
Thank you, Farid.
One last question, maybe. Any last question from the audience today before we end the session today?
I guess the last question should come from you, Shabuddin.
From me. So I hope that the question, I hope that we have a more collaboration research between your laboratory with my laboratory in UTM, Prof. Simon. I hope that is the question.
We'll work towards it.
Okay, we're going to that, because we have we also develop combustion facility here in our lab. So under Professor Cheong and so on, Dr. Cheong and so on. Okay.
Sounds good.
Good. Okay, I pass it to you, Professor Rafiq, for the close.
Okay, Shabuddin, thank you so very much. And thank you to Dr. Cheong for introducing Professor Simone Hochgreb to me. And to our distinguished speaker today, Professor Simone Hochgreb, thank you so much for accepting our invitation. and thank you so much for sharing all that you have related to combustion here. We have a team from Low Speed Wind Tunnel Lab,
Yes, yes.
which is recently being upgraded to a center of excellence. So our expectation to Dr. Shabuddin's team from this new center of Aero Lab is to make lots of collaboration with other institutions around the world. So thank you again to our distinguished speaker today, and thank you to all of you watching this webinar. I guess that's all. We do stay tuned because we have many more lectures for you. So until then, bye-bye for now. Bye-bye.
Bye-bye.
Bye-bye. Carry on.
Thank you very much.